In many statistical tests, we require a normal behavior. Even if we cannot uncover normality, there is still some merit in determining whether the distributions under comparison behave in the same manner. For some statistical inferences, a similar distribution, even if not normal, can give us an avenue to attaining and interpreting a valid comparison. We typically deploy a chi-square technique known as goodness of fit. As with Benford's law, observed results are compared against expected results. We also have variants of this process where multiple distributions can be compared against each other. These techniques are highly calculation intensive and should be left to recognized statistical programs. We make notable mention here simply to raise awareness of the connection between chi-square techniques and goodness of fit, as well as the role of goodness of fit in many statistical tests. Another application of chi-square comes through our organization of data into contingency tables. A contingency table is a table of rows and columns containing observed frequencies. The rows constitute the values of one variable. The columns constitute the values of another variable. When organized and analyzed in this manner, we can assess the dependency between the row and column variables. We can also calculate a contingency coefficient that measures the strength of the correlation. This formula is shown here. The calculated chi-square statistic is divided by the chi-square statistic plus the grand sample size, capital N. We then take the square root of this result. If the number of rows and columns is the same, we must make an adjustment for continuity and use the alternative formula given. In general, if the calculated chi-square is significant, then the contingency coefficient will also be significant. The contingency coefficient is never greater than 1 and is dependent on the total number of rows and columns. A formula for the maximum contingency coefficient is given. Here, K is the minimum number of rows and columns. Let's consider this example. We are investigating the dependency between certain foods and drinks. Assume alpha is 0.05. The null statement will be that our choice of food is independent of drink. The alternative statement will be that our choice of food is dependent on drink. The top table shows the observed frequencies for each combination. The bottom table shows the expected frequencies based on the respective column total, row total, and grand total. For example, the expected frequency for food B and drink Y will be 195 times 86 divided by 451, which equals to 37.184. Like before, retaining the precision of the expected frequencies to best calculate an accurate chi-square statistic is essential. Using the same formula defined earlier, calculate the chi-square based on our comparison of observed and expected frequencies. This number is 99.66. The contingency coefficient is 0.4253. This indicates a weak to moderate degree of dependence. Our maximum possible C would be based on minimum number of rows and columns and calculated to be 0.816. We have 5 columns and 3 rows. This gives us 8 degrees of freedom. At alpha 0.05, our critical statistic is 15.51. Therefore, we reject the null. There is a dependency between our choice of food and drink. When finding an inference about two proportions, we must have two simple random samples. Independence of samples and at least 5 successes per the earlier n times p greater than or equal to 5 requirement discussed. The configuration of the null and alternative hypothesis for the difference in proportion test follows the same format as what we have seen with difference of means and variance. The test statistic is given by the formula here. P1 hat and P2 hat are the estimated proportions. P1 minus P2 is the targeted difference. This is typically set to 0. P bar is the pooled sample proportion. Q bar is 1 minus P bar. N1 and N2 are the respective number of samples for each group. Like before, a critical Z statistic can be determined based on a known alpha and compared to the test statistic to arrive at the appropriate decision. When we are dealing with the difference of proportions that are paired or dependent, we must abandon the previous method in favor of the McNemars test. McNemars Test use frequency counts from matched pairs of nominal data from 2 categorical variables. Referring to the table here, we see we have 2 treatments and 4 respective counts, A, B, C, and D. Our null statement is that the proportions of the frequencies, B and C, are the same. Our alternative statement is that the proportion of the frequencies, B and C, are different. Our test statistic is once again based on the chi-square given by the formula shown. Note that B and C are the counts of the discordant pairs. Discordant pairs come from matched pairs of results in which 2 categories are different. In other words, yes, no, or no, yes, in this case. Pay close attention to how the data is presented to ensure that the counts of the discordant pairs are the ones used in your calculation. There is no universally accepted or required method for presenting data. Take all necessary cautions in this regard. Some important notes when running McNemars test. First, it is assumed that the sum of B and C must be at least 10. Second, the critical statistic is based on an alpha in the right tail of the chi-square distribution only. And finally, for this example, a 2 by 2, the degree of freedom will be 1. McNemars test is suited for 2 by 2 applications.